Section 8 picks up where Section 7 left off. I had started talking about rotation and had gone through the definitions for angular velocity and angular acceleration and so forth. And where we start here is the relationship between those things and the corresponding translational quantities. So for example, well, the example that's a little further down the page here, you've got a belt drive, like the serpentine belt on a car, for example, or belts are used in a number of other places. This could be the chain on a bicycle. What is the relationship? If this is the bicycle chain, what is the relationship between the speed of the chain, you know, how many inches per second or meters per second that the chain is moving? How does that relate to the angular velocity of the sprockets that it passes over? Okay, so that's the kind of thing I want to address next. So as put it about there, I guess. As a convenient way of talking about, you know, introducing these things, let's imagine some sort of a wheel that's, I don't know, mounted on the wall, okay? Like a bicycle wheel that for some reason somebody is mounted on the wall, and there's a string that's been wound around it several times, and the end of that string hangs down here, and there's a little box on the end of the string, which is a distance s from the floor. So first of all, how far? Okay, how far the wheel turns is described by this angle theta. How far the box moves is this distance s. S would be in meters, theta, well, the best way to measure theta would be radians, although there are other alternatives. The distance that's moved by the box is equal to the distance, like if you put like if you made a pencil mark on the edge of the wheel or a chalk mark or something like that. How far does that mark move? That's the same as the distance that the box moves, unless the string stretches or something like that. So this actually goes back to something I mentioned in section 7 when I explained what a radian means. I said theta in radians is the ratio of this arc length s, the ratio of that to the radius of the circle. Theta equals s over r. I've got that written again right here. That's the definition of the angle in radians. And it also provides a handy way of answering the question, if I know how far the box moves, how far did the wheel turn? Or other way around, if I know how far the wheel turns, how do I figure out how far the box moves? Well, if theta is equal to s over r, that's equivalent to saying s equals r theta. You just multiply both sides by r, and then you've got something where you don't have to deal with any fractions that way. So this is the way it's written on the formula sheet. Because this equation is the definition for what a radian means in the first place, you have to measure angles in radians for it to be true, okay? It's possible to work in other units, but this is one example of several equations that we'll see before the dust settles here, where the equation takes on its simplest form if you use radians. If you wanted theta to be in revolutions, well, you could set things up that way if you wanted, but instead of it being s equals r times theta, it would be s equals r times theta over 2 pi. Or no, it'd be the other way around. Theta times 2 pi. It would be s equals 2 pi r theta instead of just s equals r theta. You get a simpler equation if you measure in radians. And that's why, from the theoretical point of view, people usually use radians. So S equals r theta, where theta equals the angle in radians. Well, what if you're not interested in how far? What if you're interested in how fast? How does the angular velocity of the wheel compare to the angular velocity, or the regular velocity, the meters per second kind of velocity of the box? In other words, how does V compared to omega? Well, just divide both sides by the time. Distance over time is speed. Angle over time is angular speed, angular velocity. And so it follows from this that, that V is equal to R times omega. Since this is only true if you measure in radians, this will only be true if you measure in radians. So if somebody slips you an angular velocity in revolutions per minute, which happens all the time, measuring in revolutions per minute, it's a very common thing, but you have to convert to radians before you go putting that into this equation. One more step. What if it's acceleration you're interested in? Well, divide both sides by the time again. Delta V over delta T is A. Delta omega over delta T is alpha. And I'm kind of summarizing. There'd actually be a couple lines of math to write out to derive this from that. But you'd have to write this twice and then subtract to get delta V and delta omega. But anyhow, this comes from that, basically by dividing through by the time. And since this is only true if you use radians, this is only true if you use radians. A is the acceleration of the box, as in regular acceleration, meters per second squared. Alpha is the angular acceleration of the wheel in radians per second squared. Now, the distance moved by the box S is the distance moved by a point on the edge of the wheel. The velocity V of the box is the velocity of a point on the edge of the wheel. And that's fairly straightforward. With the acceleration of the box is one component of the acceleration of a point on the edge of the wheel. Like if there was a piece of chewing gum stuck to the edge of that wheel, it would, draw a picture. Probably help if I got a piece of chalk out of the drawer, wouldn't it? There's the wheel. There's the piece of chewing gum on the edge of it. The acceleration of that piece of chewing gum actually has two components. There's the centripetal acceleration that I talked about a few weeks ago, pointing toward the center of the wheel. That's what the word centripetal means, is toward the center or seeking the center. And then there's also, now if you have uniform circular motion, uniform meaning that your piece of gum keeps a constant speed, then this is the only component the acceleration has. And that's what we looked at a few weeks ago was uniform acceleration, uniform circular motion. But that's not what we're looking at now. This piece of gum is picking up speed. as the wheel goes faster and faster and faster. And that gives it this other component of the acceleration, which is equal to r times alpha, okay? So this component of the acceleration comes from the change in the direction of the velocity vector. This one comes from the change in the magnitude of the velocity vector. In other words, you get this because it's going around in a circle. You get this because it's picking up speed, okay? Well, that's what's going on with a piece of chewing gum stuck to the edge of the wheel, but that's out of focus now, of course. So we have to help it out. There we go. The reason I drew this type of situation with the little box here is because the box is unwinding along a tangent to the wheel. It's moving along a straight line. It only has the tangential component of the acceleration. So that's kind of uncluttered by the centripetal thing that's also going on up here. So anyhow, that's just some background information. Basic idea is AT is the acceleration of the box, alpha is the angular acceleration of the wheel. For the velocity, tangential velocity, I didn't really need the subscript. Maybe I should have just left it off for simplicity. As long as you're talking about something traveling along a circle, the tangential component of the velocity would be the only component it has. The only time you'd get a radial component would be like if you were talking about a satellite on an elliptical orbit or something like that. But this is just the speed of our piece of chewing gum, which is the same as the speed of the box. And one more time, anytime you use one of those, you have to have radians. And I tried to remind you of that on the formula sheet. I have the formula sheet right here. On the top of page 3 is the 3 formulas I just introduced you to. And in capital letters, I put use radians. So don't say I didn't warn you. Maybe I should have put it in like a larger font in boldface red print or something like that. And there would still be people who wouldn't do it. But anyhow, try not to get caught by that. So I do an example, and then I've got like half a page of examples for you to work on, because this kind of builds on the stuff at the end of the previous unit also. But first of all, I'm going to do this one with the belt drive that I called 8A. So the first part asks to find the speed, or I guess technically the right word would be the speed of the belt. For both parts of this, what we're going to use is V equals R omega. This thing here that is almost but not quite disappearing off the top of the picture. I know, yeah, the small one. I know the angular velocity of the little wheel. Tells me over here it's spinning around at 500 RPMs, okay? And what it asks me for is V. So if I know the radius, which is given on the picture, and I know omega, I can solve for V. And that's kind of the general idea. There's some details I'll write out in a moment, but that's part A. For part B, it asks for the angular velocity of the bigger wheel. Well, the thing here is that after I've done part A, we'll know that the belt is moving at a little over 2.6 meters per second. The speed of a point on the edge of this wheel is the same as the speed of a point on the edge of this wheel, at least if it's working properly. The belt is not supposed to slip. Once in a while you hear a car go past you that's making all kinds of terrible noises because they don't have enough tension on a belt, and it's slipping and it squeals, but If the thing is working right anyhow, there's no slippage. And so a point on the edge of this wheel has a speed that's equal to the speed of the belt, and a point on the edge of this wheel has a speed which is equal to the speed of the belt. So the answer to part A tells us V for a point on the edge of this wheel, and we know R, so we can solve for omega. So that's the general idea, and the details look like this. Chords are already catching on things. A little further that way. Like that, okay. Equals R omega. We're going to apply it to the little wheel. Little wheel has a radius of 5 centimeters. There's the belt going across the wheel. The belt is moving with a speed v, which we assume equals the speed of a point on the edge of the wheel. What the v in the equation actually stands for is the speed of a point on the edge of the wheel. If the belt was slipping, the speed of the belt and this v here would be two different things. But like I said a minute ago, it's bad when the belt slips. The belt is not supposed to slip. So the speed of the belt should equal the speed of a point on the edge of the wheel. And this v is what the question asks for. Well, the question doesn't specify units. So I could leave the radius in centimeters, and if I did that, then the speed would come out in centimeters per second, and that would be okay. If you did that on, if this was a test question, I'd give you full credit for that. But I feel like being prim and proper and using the standard unit, so I converted that to 0.05 of a meter. Now, the angular velocity. The question says this wheel is spinning around at 500 revolutions per minute. So there are people who would answer the question by multiplying 500 times 0.05, but you're not one of those people, are you? Revolutions are no good. You have to have radians. When in doubt, convert to radians. It's not always necessary, like those equations at the end of section 7. They work just fine. They're very easygoing equations. They work just fine if you measure in revolutions or degrees or make up your own unit for angles. As long as you're consistent about it and use the same unit all the way across the equation, everything is fine. But there are other equations that are more particular, and this is one of them. If you're not sure which ones are which, convert to radians. Like I said, not always necessary, but it's never actually wrong. There are no equations where you can't use radians. Anyhow, for this one, you have to have radians. As far as minutes, well, I guess there's nothing in the question that says you couldn't express the answer in meters per minute, but again, I'm feeling like using the standard units, so I'm going to convert to seconds. And we did some of this sort of thing at the end of section 7, so hopefully this is fresh in your mind from that. To convert units, you multiply by a fraction where the top is equal to the bottom, set up in a way that makes the unwanted unit cancel out. Minutes divided by minutes goes away. Two pi radians equals 1 revolution. So there again, a fraction where the top equals the bottom, you multiply by that fraction and you set it up in a way that makes the unwanted unit cancel out. Revolutions divided by revolutions goes away. And that's how you figure out that you should be dividing by 60, not multiplying. And that's how you figure out you should be multiplying by 2 pi, not dividing. So now it's all set up. If anybody cares, this is 52.4 radians per second, but well, if I wasn't talking to a bunch of people about it, I wouldn't have bothered writing that down. I would have just kept on multiplying, thrown in the 0.05, and after you do that, that times that is 2.62 meters per second for the speed of the belt. Part B, I suppose I should have labeled this, Part A, Part B. The belt makes V, meaning V for the large wheel, the same as for the small pulley. So here's the big pulley. Got a radius of 20 centimeters. We have established that the belt is moving at 2.62 meters per second. So if V is equal to R times omega, divide both sides by R, and that becomes omega equals V over R. Fill in the numbers. Point on the edge of the wheel moves 2.62 meters per second. The units, of course, have to match. If you've got meters per second here, this has got to be meters. You can't have meters one place and centimeters the other, or you'll make a decimal error. Now, Meters cancels meters, leaving you with actually no unit at all. I explained in section 7 how a radian is not a unit in the same sense that a kilogram or a newton is. An angle in radians is actually a dimensionless ratio, okay? So usually written radians per second, but really it's empty numerator per second is what you've got. It's just seconds. You could write it like this. Seconds to the -1 power. The question doesn't ask for this, but if you convert it back to revolutions per minute, because maybe you find that more meaningful, that's equivalent to 125. So the little one is going around at 500 revolutions per minute. The big one is going around at only a quarter of that rate because, you know, it's 4 times as far to go around the edge of that bigger wheel. So every time this one goes around once, it only moves enough belt to make this go a quarter of a turn. So this one's spinning around faster, this one's spinning around slower in terms of their angular velocities. The regular velocity, you know, V rather than omega of the belt is the same as it goes across both of them. Okay. Well, I guess you can see the first example without me boosting the picture up any further. Maybe if I try and focus it a little bit. Where people usually go wrong, or let's say, I don't know, there are other ways to go wrong also, but let me try again with the focus. A popular way of losing points anyhow is a question will tell you something like, that just does not want to focus. If I go closer. Question will tell you something like, you know, angular velocity is 52 radians per second. That's what we had in that part A of the one I just did. And the student starts writing on their paper, given V equals 52 radians per second. And no, that's wrong. There's no way you're going to get the right answer. You've messed it up on the first line, okay? If it's radians per second, it's omega, not V. So I thought it might be useful to start out with a little exercise matching the numbers to, well, actually, it's not the numbers that are the point, it's the units, matching the units to the letters. So pause the recording and write down what you think each of these are. You know, it's like a matching thing. Match these letters to these numbers. And what you want to be looking for, if you need a hint, maybe you've already paused it and written down all the answers. If you get them right, that would be great. But first of all, there's the 3 regular Roman letters versus the 3 Greek letters. The difference is these, the regular letters, would involve some kind of a distance unit. In this course, it would typically be meters. You know, that's the official SI unit, but it could be feet or miles or centimeters. But some kind of a distance unit is in there if it's S, V, or A. If it's a Greek letter thing, then there'd be an angle unit instead, like revolutions or radians. That's why it's called angular velocity and angular acceleration. is because of that. So distance units, angle units, and then if it's how far distance s, how far angle theta, it would be just the distance or angle unit. If it's divided by time, that's some kind of a speed, either velocity or angular velocity, depending on what's the unit up above the time. If the time is squared, then you've got some sort of an acceleration, either a or alpha, okay? So that's what you need to keep in mind. If you haven't already done so, pause it, try to figure it out for yourself. And now I'll give you the answers. So first of all, and maybe a little further down, you had 5 meters per second. Distance over time is velocity, not angular velocity. That would be angle over time. So this gets a V. Next one to the right, we had 7 radians. Well, a radian is a unit that you measure angles with. And there isn't any time unit underneath of it, so it's an angle, it's theta. Been using theta for angles since probably section 2. Next one was 8 revolutions per minute. So that's some kind of velocity because it's divided by the time. It's an angular velocity because a revolution is a unit you can measure angles with, okay? A wheel turned a quarter of a revolution, a wheel turned 90 degrees, it means the same thing. So angle over time is angular velocity. On the end here, we had 3 radians per second. Also angular velocity. Once again, an angle unit divided by a time unit. And then there was 4 meters. That's a distance. Early in the course, I was using delta X for that, but more recently it's been the letter S. Then we had 9 meters per second squared. The time unit is squared. That makes it some kind of an acceleration. But it's not an angular acceleration because, you know, you can't draw a 4-meter angle. A meter is a unit of distance. You can talk about how many meters I'm standing from the door. So A, not alpha. 12 miles an hour. Distance over time. Same as back up here. Meters is distance, seconds is time, miles is distance, hours is time. Velocity, V. And the last one was 6 radians per second squared. So once again, as with this one, it's some kind of an acceleration because the time is squared. What's on top this time is an angle unit, which makes it an angular acceleration. It's being stubborn. Got it. Okay. So you've got a wheel rolling, you know, this could be a wheel on a car or a bicycle. It's going down the road at 15 meters per second without slipping. Now, like I said in the one about the belt drive that I did a couple of minutes ago, but what I said in that one is if there's no slippage, the speed of the belt is the same as the speed of a point on the edge of the wheel, which is what the V in the formula stands for, a point on the edge of the wheel. Well, it's the same thing here. As long as there is no slippage between the tire and the road, then if the car is going down the road at 15 meters per second, then a point on the edge of the wheel is spinning around the center of the wheel at 15 meters per second. If there's slippage, like if you lock up the brakes or something, then those would be two different speeds, but that's not happening here. So you want to find the angular velocity. Well, I should probably try to let you figure this out for yourself before I say too much. So pause it, work on it. And if you need help, help is on the way. And as I've probably said too many times already, if you do need to watch me do it because you weren't able to do it yourself, after you've watched me do it, you should probably pause the recording again and see if you can do it yourself now. Because if you can't do this, there could probably be something on a test that's coming up that you won't be able to do. Number 2. Here's the wheel. And imagine it's a 4-lane or a 6-lane road or something, so that you're in one car looking out the window at this other car that's in the next lane over. So you're going the same speed as this other car. You're at rest relative to the center of the wheel. Seen from that frame of reference, the edge of the wheel is going around the center with a speed v. Okay, this point's going that way at a speed v, this point's going that way, 15 meters per second is the question tells us that. So seen from this frame of reference, that's what the wheel is doing. Back in section 1, I told you that a good way to start a problem is to make a list of what you know and what you're looking for. And that's even more important now. Back then, you know, V for velocity, that was fairly straightforward. Now you've got all these weird looking symbols. So take the time to carefully think it through, look for hints on your formula sheet that'll help you out. And 15 meters per second is V, not omega. That was the point of this first one I did. We told the radius. The question says, find its angular velocity. So you know those two things, you're looking for this thing, and you look around the formula sheet for an equation that contains just those three things, and you find one. This would be part A of the question. V equals R times omega, which same thing I did to it before. since it's omega, I want to know omega equals V over R. Divide both sides by R. Convert the 40 centimeters to 0.4 of a meter, because the units have to match so that they'll cancel each other out. And it comes out 37.5 radians per second. It's in radians per second because, well, the seconds come from here. The velocity was in meters per second, so that carries through. As for the radians, it's built into the formula that it's in radians. Part B asks for the equivalent number of revolutions per minute. And this is just a unit conversion similar to others that you've done before. In fact, it's not exactly the same as the one that I did with the pulley a few minutes ago. There, you started out with revolutions per minute, and we're trying to convert into radians per second. Here, it's the other way around. You're starting out with radians per second. So it's the same conversion factors, but this time they're all upside down compared to that one back over there. Since radians is on top, you want radians on the bottom, so that they'll cancel. Revolutions you want to have to replace it. 1 revolution equals 2 pi radians. And with the time units, seconds is on the bottom, so you want seconds on top. Seconds over seconds cancels that way. So 37.5 divided by 2 pi times 60, 358. Next one. Oh, how nice it's focused. So number 2 was about velocity and angular velocity. Number 3 is about acceleration and angular acceleration. So part A says to find the tangential acceleration of a small stone stuck in the tread of the tire. Well, if you think you can get it, go ahead. But if you need a hint, which I have found a lot of people do at this point, it goes back to what I was saying about how if the wheels don't slip, then, well, in number 2, it was the velocity I was talking about. The V in V equals R omega equals the speed that the car is going down the road. In the same way, if the wheels don't slip, then the tangential acceleration of a point on the edge of the wheel equals the acceleration of the car. So to get, part A, find the tangential acceleration of this little stone. That's equal, because the wheels don't slip, there's no skidding going on or anything. This is equal to the acceleration of the car, which there's enough information here to figure out. Once you have the tangential acceleration, you can get the angular acceleration from that. So if you didn't already get it, pause it here and figure those out for yourself. And while you're doing that, I'm going to erase the left hand into the blackboard. Part A. The tangential acceleration of a point on the wheel equals the acceleration of the car as it accelerates down the road. From the first day of the course, acceleration is delta V over delta T. The car goes from 0 to 30 meters per second. That makes the change 30. 15 seconds. 30 divided by 15 is 2. Meters per second per second. B. The angular acceleration of the wheels. Well, the acceleration of the car equals the tangential acceleration. Of course, the little stone also has a centripetal acceleration, which comes from a whole different formula. That's equal to v squared over r. But this component of the acceleration is equal to r times alpha, and it's alpha the question asks for. So fill in the answer from the previous part of the question for the acceleration. And the radius has to be in meters. Well, either that or you have to convert this to centimeters per second squared. It'll work either way, but they have to match. Meters cancels meters, leaving you with radians per second squared. 5 of them. Five radians per second squared. Number 4. Four is a long one. Between part A and part B, it asks for 6 different things. Here's the clue I'll give you right at the beginning. A little bigger. Part A asks for 3 things, part B asks for 3 things, 6 answers altogether. 1 or more of those answers is actually just given information. Not everything the question asks for requires you to do anything to get it. There is some of this where I'm just looking to see if you recognize certain quantities when you're looking at them. So we've got a wheel mounted on some sort of horizontal axle, string wound around it several times, a box hanging off the end of the rope. And I guess this is where you should pause it and see how far you can get on your own. And now I'm back. And I'm going to go through just part A in case you've seen part A. Maybe that gets you going and you can do part B on your own after that, if you couldn't before. So the first thing it asks for is the angle it has turned. Part A. So what is theta when it is turned 30 revolutions? 30 revolutions. And I see people sometimes who feel the need to convert that into degrees or maybe revolutions, and well, doesn't hurt anything, but the question didn't specify what unit to give the answer in. So the easiest thing to do is just leave it in the unit that it's already in. Continuing. 30 revolutions after starting from rest, the wheel is turning at 40 revolutions per minute. So at this time, at the time that it's turning 40 revolutions per minute, its angular velocity is 40 revolutions per minute. Also given information. I called it omega final because this is how fast it's spinning at the end of that 30 revolutions. And we're supposed to, well, at this time find the angular acceleration. It's the same angular acceleration throughout the whole process. You have, you know, the weight of the box stays constant, and the amount of leverage that the force from that, you know, the force of that weight gets would be the radius of the wheel. That never changes. So you have, well, I haven't actually gotten to torque yet. That's coming up soon, but you've got a constant amount of torque acting on the wheel. That's going to create a constant angular acceleration. So initial equals final equals average. And because the angular acceleration is constant, that list of equations from the end of section 7 will apply. So I should probably write out another one of those little lists, but I've got most of it here. We know this. We know this. We also know that at the beginning of that 30 revolutions, it's at rest, 30 revolutions after starting from rest. So we know those three things, and we're trying to find alpha. And so you look for an equation that contains this, 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 and alpha. So you can solve for alpha, and that's this one. Omega final squared equals omega initial squared plus 2 alpha delta theta. And there's other ways of doing it also. If you did it some other way, your way is not necessarily wrong, but I think this is the quickest way, quickest, most efficient way to get to the answer. Now, this is not one of those equations where you have to have radians. Although, like I said, when in doubt, convert to radians. And actually, by the time you're done with part B, it won't even be wasted effort. But if all there was part A, you can leave it in the units you were given and it'll work. So for omega final, we had the 40 revolutions per minute. Omega final squared equals omega initial squared plus 2 times alpha times delta theta, which was the 30 revolutions. Revolutions here, revolutions there. I'm being consistent with myself. That's all that matters. 40 squared is 1600. The units get squared along with the number. Over here, revolutions times a dimensionless number gives you something in revolutions. Then to solve it for alpha, you divide both sides by 60. .6.7. As for what that's measured in, well, when you divide, this revolution here cancels one of those revolutions there, and you're left with revolutions per minute squared. Or I have the answer written here in several other combinations of units. If that's what you happen to work in, this is equivalent in revolutions per second squared. That comes out 0.00741. In radians per minute squared, it's 167. And in radians per second squared, it's 0.0465. So there's the answer to that in a wide variety of different units. So I'm going to suggest that if you weren't able to get part B, well, let me throw you a couple of hints first of all. Now that we've got theta, omega, and alpha all written out in part A, let's punch you back over here at the upper part of my handout. So, you know theta and omega and alpha, and the question's now asking you for distance, velocity, and acceleration for that box. So what equations do you suppose you ought to be using? Well, pause it here, work through the details. As soon as I get a little more of the blackboard erased, I'll write them out. Part B. First of all, the distance, that's got to be a really long rope, because this comes out 113 meters. That's like 325 or 350 feet, something in that neighborhood. But aside from any question about how realistic the numbers might be, we've got S equals R times theta. S means the distance, well, it means the distance a point moves on the end of the edge of the wheel, which is going to be the same as the amount that the box goes down, assuming that the rope doesn't stretch or anything like that. So it's asking us for S. The radius of the wheel is given, it's written on the picture. Theta is the answer we got back here to part A, the 30 revolutions, except this is one of those equations where you do have to have radians. So if you just, and this is a common mistake, there's no shame in making it, just try not to make it when we get to an actual test. If you just went 0.6 meters times 30 revolutions, and that wasn't, what do you get, 18, I guess, if you do that? Yeah, the thing that's wrong with that is you're off by a factor of 2 pi. So 30 revolutions times 2 pi radians per revolution. So like that. And it's about 188.5 radians. That's what you have to put in for theta. S equals R theta, where theta is in radians. So 0.6 of a meter So once again, an angle in radians is actually just a dimensionless number. Meters times a number with no unit on it gives you meters. The second one, the speed of that box at the end of that 30 revolutions. At that particular moment, it's moving at 2.51 meters per second. Or there's nothing in the question actually that says you have to measure time in seconds. If you left it in minutes, it would have been 151 meters per minute. But seconds is kind of the standard way of doing things. Once again, you've got to have radians for the equation to be valid. And I converted the time into seconds just because I wanted to. So that was 40 revolutions per minute. That was omega final. And these unit conversions are getting kind of tedious and repetitive, I suppose, but I kind of think some people at least need the practice. So doing the same thing that I've done several times at this point. 40 revolutions per minute is equivalent to 4.189. 4.19 is close enough, really. That's, I should have written the unit next to that. Radians per second. Once you've got the units straight, velocity is equal to R times omega, which is 0.6 of a meter times the number that I just came up with. And once again, as far as how the units work, a radian is not really a unit, it's just a dimensionless ratio. You've got meters here, you've got per second there. You put them together, meters per second, 2.51 of them. And it's the same sort of story again with the angular acceleration. You got to straighten out the units, and then you can put it into A equals R times alpha. So from back here, we had, well, to be precise, it was 26 2/3 revolutions per minute squared. Revolutions cancel out, so you'd have radians per minute squared. 1 minute. Now, tricky point. Minutes to the first power does not cancel with minutes squared. You've got to divide by 3,600, not by 60. 0.0465. So the equivalent number of radians per second squared is that. A is equal to R times alpha, AT to be precise, the tangential component of the acceleration. 0.6 of a meter times 0.46. Or again, the question didn't really say you had to stick to standard units. If you had it in meters per minute squared, that is equivalent to 100.5 of those. Now, how much of this is left? Do I want to try and go all the way through it, or do I want to try and do it all, or do it in 2 recordings? Yeah, that'd probably only take another half hour. Let's do it all in one chunk. Of course, anytime I think something's going to take it half an hour, it always turns out to be at least an hour. Like I can't even brush my teeth without it taking twice as long as I thought it ought to. Anyhow, rotational kinetic energy. Yeah. There we go. So continuing to parallel what I did earlier in the course, after going through the basic definitions, velocity means this, acceleration means that, and so on, we started talking, well, did a couple of other things also along the way, but within a few weeks, I brought up the idea of kinetic energy, which means the work that an object could do because of its motion. Well, something that's spinning around can do work, just as something that's moving along a straight line can do work. How much work can a rotating object do? Well, I'll explain it to you. Let's start out with what we already know. and kind of build off of that. The simplest case would be a small point-like particle, something kind of like that lab where you spun the rubber stopper in a circle over your head, or maybe if you were smart, you got your partner to spin the rubber circle or rubber stopper in a circle over their head. Anyhow, some object small enough that its size is negligible compared to the radius of the circle it's going around in. It's moving at a speed v, and as we saw earlier in the course, that means it has a kinetic energy of 1/2 mv squared. It can do this much work. Let's make a few substitutions. First of all, v is equal to r times omega. That should sound familiar. I just spent like an hour going through examples that used that. There is a catch. V is only equal to r times omega if you measure omega in radians per second squared. So what we come to based on this is going to be something where radians are required. If you use revolutions, it makes this step invalid, which makes the result invalid. So another one where you have to use radians. When in doubt, convert to radians. So V is equal to R times omega. R omega squared would be equivalent to R squared times omega squared. And then I kind of slip a new set of parentheses in there around the MR squared. That, for reasons I'll get to in a minute or two, is called the particle's moment of inertia, mr squared. So substituting in the letter I, where the mr squared used to be, I for inertia, we have that the kinetic energy of that little particle is 1/2 I times omega squared. Now, occasionally you're talking about a point-like object going around in a circle. Much more often, you're talking about some sort of extended object, like a lawnmower blade that's spinning around, or the gears inside of a transmission, or a door rotating around its hinges, or some sort of extended object like that. So to apply what I've already said to something like that, think of that object as a whole bunch of little particles like this one stuck together, okay? Here we have a mass M1 at a distance R1. As far as what this blob is supposed to be, it's just some generic rotating object. It could be a very badly drawn gear spinning around in a transmission. It could be a very badly drawn door rotating around its hinges. In that case, you'd be looking down on the door from above or up at it from below. Whatever, if it's a door, you just think of it as being a bunch of pieces of sawdust that just haven't been separated from each other. And so there's one little bit of sawdust there. Its mass is M1, its radius is R1, or the radius of its path, I mean. It goes around in a circle, the radius of that circular path. Another piece M2, which is going around in a circle of radius R2 and so on. You divide up I didn't draw all the little pieces, but you divide up the whole body like that into a very large number of very small pieces, add up the kinetic energy of each little piece to get the kinetic energy of the whole object. Well, you've got this summation of many, many terms, kinetic energy of the first piece plus the kinetic energy of the second piece plus and so on. For each of those terms, the 1/2 is a common factor, and you can factor it out. Omega is a common factor. Every piece of the object goes around with the same angular velocity. If different parts of it had different angular velocities, it would have to break up in order to do that. So you factor out the common factors. And you've got 1/2 times omega squared times the summation of the mr squareds summed over all these little pieces. So to get the total inertia of the entire object, add up mr squared for all of its pieces, and kinetic energy is 1/2 I omega squared, where I stands for this, what you get when you do this summation. What that adds up to depends on the object's shape, okay? If you, well, I got the formula sheet right here. Section 8. If you have a point-like particle, I is equal to mr squared. The little r here does not stand for the radius of the object. I'm assuming the radius of the object is 0, okay? A very small particle. R is the radius of the path it follows. And as for other sorts of things, well, if you have a hoop, all of the pieces, maybe I should draw a little sketch. A hoop or a piece of pipe would just be a very, very long hoop. If you've got a thin-walled piece of pipe rolling across the floor, all of the mass is at the outside edge. So if you divide this up into lots of small parts and add to get the total inertia of the whole thing, well, R is equal to the outside, the radius to the outside edge for every one of them. And so you get, as it says in very fuzzy writing there it goes, right up at the top of the list there. For a hoop or a tube, I equals mr squared. Now, next one down, if you've got a solid rod instead of a piece of pipe, okay? Or the way it's written there, a solid cylinder or a disc, only 1/2 mr squared, because if instead of having all the mass at the outside edge, if it's all the way, if it's a solid object all the way from the center out, well, you start breaking it up into little pieces like I was talking about, and most of the little r's are less than the capital R. In other words, most of the mass is located closer to the center where it contributes less inertia. And that's why if it's a solid disk, it only adds up to 1/2 mr squared. Whereas if it's a hoop with all the mass at the outside edge, it's 1 times mr squared. And if you distribute the mass in other ways, you get other relationships. For a solid sphere, it's 2/5 mr squared. For a thin spherical shell, it's 2/3 mr squared, and on down the list on the formula sheet here. So if you're talking about translational motion, okay, if you're just going to push a glider down an air track, then the inertia is determined by the mass. The mass is the inertia with respect to motion along a straight line. But if you try to make something rotate, the inertia depends not only on how much mass is there, but on how it's distributed. The farther the mass is from the axis of rotation, the more inertia it has. If you've ever carried a long ladder, like an 18-foot extension ladder or something like that, or a very long board, some board that's 12 feet long or something like that, you may have noticed that if you walk around the corner of the house so that you have to rotate the board, because first you're walking toward the east, and then you're going to go around the corner, and then you'll be walking toward the north, and you got to turn the board as you make the turn there. You might notice that it seems rather difficult to make that board start to rotate. And once you get it going, it's hard to make it stop again, compared to if you just had like a suitcase full of stuff that weighed the same thing. You just, all the mass is within just a foot or two of your hand. You twist on it, it's fairly easy to make it start spinning around, kind of like that. Whereas if you have the same amount of mass, and most of the mass is way the heck out there, 5 or 10 feet away from you, well, at those large distances, you have to get those parts of the object up to a pretty high speed. I mean, if you're driving around the country and you look at a wind turbine, and it's like, they're going around nice and slow, and it's sort of majestic looking. Yeah, the tips of those blades are going something like 180 miles an hour. Because if you got close to those things are big. And to get around such a big circle at even like 2 or 3 revolutions per minute, the tips of those blades are going fast. So if you're trying to make a board rotate as you walk around the corner of the house, out near the end of the board, you have to get it going fast. And a high velocity V to get up to a certain angular velocity, omega, well, getting it up to that high speed requires more effort than if you had everything in close, where you don't have to get it going very fast to make it spin at the same rate. Okay, so that's kind of the reason why, in words, without resorting to equations. But any way you want to look at it, less inertia, less rotational inertia. When the mass is in close, more rotational inertia when the mass is farther out. So what this summation adds up to depends on the object's shape, as I've just described at maybe greater length than I really needed to. I don't know. I'm going to do an example, and then you're going to do 2 examples. Well, one of them is more of a conceptual question, and that takes care of section 8, because if you turn the page, that's the review for the next exam on the back there. So in this one, we have what amounts to a system of 2 small particles, heavy but small, okay? You've got 1 kilogram here, you've got 2 kilograms over here. We're assuming that the diameter of each of those objects is quite a bit less than the 10 or 20 centimeters. That's the radius of the circle they follow as they spin. There's some sort of lightweight rods here. It says the rods have negligible mass, so it's some sort of high strength graphite, carbon fiber kind of material that there's only a few grams there, not enough to contribute to the inertia in any meaningful way. So it's a conservation of energy problem. You start out with everything at rest, and there's this little box that's elevated off the floor, so it's got some potential energy. The box hangs from a string that's wound around a very small pulley here. The little wheel is small enough that it doesn't contribute any significant inertia of its own. And so also the box hits the speed hits the floor with a speed that's small enough that, because the radius of this wheel is so small, you do r times omega, and the speed of the box is quite small, so we don't have to worry about the kinetic energy of the box. Almost all the kinetic energy in the end is the rotational kinetic energy of these two objects circling around like that. So the potential energy it starts with equals the kinetic energy that's there in the end, and that's the basic idea behind it. And the details look like this. So I'll go through this one, and then there's a conceptual problem, and then there's a quantitative problem that's a little bit like the one that I'm going to go through here. Part A. Well, kinetic energy equals 1/2 I omega squared. So I'm going to need the moment of inertia. So I might as well get that figured out right at the beginning. Get a number for it that I can use when I need it. The moment of inertia of a point-like particle is mr squared. If you have a system of point-like particles, it's the summation of those mr squareds. Well, if it's a hoop or a disc or a sphere or something, the summation has like a bazillion terms in it because you break it up into a very large number of very small, well, for those of you who've taken calculus, you integrate is what you do. Take the limit of infinitely many, infinitely small particles. But in this case, there are only two particles. So it'll just be mr squared for the one plus mr squared for the other one. So the numbers work out to 0.06 as far as what it's measured in. Units of mass times radius squared. Kilograms times squared meters. Quite often the SI system gives a special name to a combination of units like this. This is not one of those times. Nobody has ever given a name to that unit. It's just kilograms times squared meters. It comes right down to it. Who would want a unit of inertia named after them? And could be taken in a kind of an unflattering way. It's like, yeah, we're going to name this unit after Fred because Fred never gets off the couch. He has a lot of inertia. He never moves. So we'll just call it kilograms square meters and not name it after anybody. So with that ready to plug in when we need it, we're assuming a frictionless situation here. So therefore, the potential energy that you start out with equals the kinetic energy that you end up with. Start out with everything at rest. In the beginning, there's no kinetic energy. It's just the potential energy of that elevated box. When the box gets to the floor, there isn't any potential energy left. But now these two masses have kinetic energy as they orbit around. And again, we're assuming that the box is going so slowly because it's unwinding off of such a small spool. It's going so slowly, there's very little kinetic energy in the box. We'll just overlook that and say that it's all in the things that are going around in a circle. MGH, half a kilogram for M. G is 9.8. It starts out 0.3 of a meter above the floor. And you solve it for omega. That times that times that is 1.47. Half of 0.06 is 0.03. Divide and then take the square root. The numbers come out 7 even. It's built into this formula that omega is in radians, well, radians per whatever time unit you're using. And the 9.8 was in meters per second squared, so that's where the seconds come from. Okay. Back over here. Raise the note packet a little higher. Number 5 is one of those conceptual questions like you would find at the end of one of my exams. Solid disc, like a slab cut out of a telephone pole. Thin hoop, like a bicycle wheel. The spokes have so little mass, you might as well overlook it. Practically all the mass is on the outside edge. Both of them have a string wound around them. There's the same amount of weight hanging off the end of both strings. They both start from rest. The boxes fall the same distance. Basically, everything that you can think of is the same, except for the fact that this is a disc and that's a hoop. But the mass is the same. You know, if this disc is 1.1 kilograms, the hoop is also 1.1 kilograms, and it's the same radius to the outside edge of them. So compare the final angular speeds. In other words, which one ends up spinning faster? Pause it for a moment and form an opinion. And here comes the answer. It's the disc that ends up going faster. Solid disc is faster because, well, inertia means sluggishness, right? The more inertia something has, the more it resists acceleration. And we'll look at how acceleration is involved coming up in section 9, if I remember right, sometime soon anyhow. But more inertia means more sluggishness. If it's at rest, it's hard to get it moving. If it's moving, it's hard to make it stop. The more inertia it has, the greater the extent to which that's true. So the disk is the one with less inertia, meaning that, well, you know, if you go back to something like this, if you want to think of it in terms of energy, in both cases, you start out with the same potential energy because you've got identical boxes at identical distances off the floor. The one for which I is small, so you got the same thing to the left of the equals. Over here to the right of the equals, the one for which I is smaller will be the one for which omega is bigger, so that it multiplies out to the same thing. Or just in words, something that's less sluggish is going to pick up speed more rapidly. I is less for the disk. You can look up the formulas on the formula sheet, 1/2 mr squared for a disk versus 1 times, I guess I'm off the edge of my picture, 1 times mr squared for the hoop. Or, you know, just in terms of the underlying idea, more inertia where the mass is farther out. And in the hoop, most of the mass is farther from the axis of rotation than you'd have in a solid disk. One more for you to work on. We have a yo-yo, which we're going to say has a mass of 100 grams. It might be a little on the high side, but probably isn't too far off. And its moment of inertia is there. If you need a hint, this is once again a conservation of energy problem. It's just turned around compared to the one that I worked through a couple of minutes ago. In that one, you started out with some potential energy that got turned into kinetic energy. Here, you start out with some kinetic energy, which is turned into potential energy as the yo-yo climbs up the string. So you just need to solve for the final height, assuming it starts at 0. And pause it here. And now here's how I did it. So when it's at the bottom of the string, it's spinning around and therefore has some rotational kinetic energy. As it climbs the string, that kinetic energy turns into potential energy. Fill in the numbers. Well, to keep it kind of short and sweet, the question tells us the moment of inertia rather than making us figure it out from the mass and the radius. It's 1.2 times 10 to the negative 4 kilograms times squared meters. And it's spinning at 70 radians per second. One half I omega squared. Over here, mgh. Mass is 1/10 of a kilogram, given in the question. G is its usual, 9.8. H, the height that it climbs to, is what I want to know. That times 70 squared comes out 0.294. 0.1 times 9.8 equals that. Divide, solve for H. So you divide both sides by the 0.98. It comes out 0.30 of a meter, 30 centimeters. And in the next recording, we will start on the third and final packet of notes. The third handout does sections 9 through 14.